Hi, my name is George Danish from the University of Cambridge, and this is the virtual SIGGRAPH 2020 presentation of our model of motion quality for rendering with adaptive refresh rate and resolution. I hope you enjoy it. As we all know, modern displays are reaching ever better capabilities, providing resolutions at Full HD, 4K, 8K, 16K. You look away for a second and probably someone will release 32K. On the other hand, refresh rate is also steadily increasing, with VR headsets and monitors designed for video games reaching 90 to 360 Hz compared to standard 60 Hz rendering. The main issue is that GPU performance and transmission bandwidth do not scale equally quickly. Going from Full HD 60 Hz rendering, which is the setup I, among many, would normally use, to 8K 240 Hz requires 64 times the computation, memory, and bandwidth. You go for 16K, and this multiplier goes up to 256. Therefore, GPUs often can't make full use of the latest displays, and a compromise has to be made. The question is then, how should we trade off resolution for refresh rate? In today's presentation, this is the question I will try to answer. First, I will explain the scope of our work before giving an overview of how we, humans, perceive motion. Then I will introduce the visual model we propose for predicting motion quality. Lastly, I will describe how we evaluated this model by driving the refresh rate resolution trade-off in a video game setup. So let me start by further analyzing the question of how should we trade off resolution for refresh rate. First, there is a technological aspect. Can I pick an arbitrary refresh rate and resolution and use it at any time? Luckily, with G-Sync and FreeSync, the answer is yes, or at least almost yes, with perhaps a bit of space for improvement in the communication between the GPU and the display embedded chip. Second, we need to consider human subjective preference. Do humans actually prefer blurry content, which moves smoothly, or leggy, high-resolution content? Also, are they happy with this trade-off changing in real time? As it turns out, the answer is application-specific. Especially for movie content, humans are extremely biased towards low refresh rate. Hence, our work investigates the latter question in the context of the less explored area of video games only. So let's see how we perceive the quality of a moving object when we reduce the resolution and the refresh rate. Now, reduced resolution results in blurry or aliased images, depending on your sampling strategy. Motion artifacts, due to limited refresh rate, however, come in multiple flavors. Dali et al. Identified 4 types of artifacts to be precise: flicker, false edges, motion blur, and judder. Let's look at the tennis ball on the right, and while the motion quality of video streaming is already rather limited, let's assume it is undergoing perfect motion at this moment. Flicker occurs when the luminance of the screen changes in time. This could happen due to backlight dimming or when using low persistence displays. If the temporal frequency of the change is below a certain frequency threshold, called the critical flicker frequency, human observers will see highly objectionable flicker artifacts. False edges also occur in temporally changing displays, where the rate of change is too fast to be perceived as flicker, but the eye can't actually integrate a continuous image. Such artifacts are often visible when using DLP projectors or during saccadic eye motion on low persistence displays. Blurring occurs when looking at moving targets. The eye tries to match the speed of the object with its smooth pursuit eye motion or span mechanism, but a display shows a discrete sequence of stationary frames. As the eye is continuously moving, the temporally stationary objects blur on the retina. At low refresh rates, the full illusion of smooth motion can break. This creates juddery, stuttery, or strobing motion. In our work, We use high persistence displays and therefore decided to focus on blur and judder artifacts. Before we started building our model, we wanted to understand how important exactly refresh rate is. There's plenty of proof that 60 Hz provides better quality than 30 Hz, of the same spatial resolution at least. Noland identified the critical refresh rate beyond which no improvement is perceivable. However, there has been no extensive research on the quality of animation above 60 Hz. We therefore conducted a psychophysical experiment with 11 participants, asking them to compare the quality of motion when looking at synthetic stimuli undergoing various motion patterns and different velocities. This includes refresh rates from 50 Hz all the way to 165 Hz at a granularity of 5 Hz. We used a side-by-side pairwise comparison design with 2 identical displays showing the same content and different refresh rates. To reduce the number of comparisons, we utilized active sampling. Cross-velocity comparisons were also made for one content. We found a few interesting trends when plotting the quality curves of different object velocities as a function of refresh rate. First, refresh rate remains important well above 120 Hz. First, refresh rate remains important well above 120 Hz. For example, there's usually a 1 JND difference between 120 Hz and 165 Hz. Now, 1 JND means that 75% of the population is able to spot the difference and identify 165 Hz as being better. Secondly, refresh rate seems to affect lower velocities more than higher velocities. This is somewhat counterintuitive, as blur artifacts are stronger on higher velocities. We speculate that this could be due to judder artifacts, as non-smooth motion can be more visible at lower velocities. Hence, as I mentioned, we include both components in our model. We also found that when the eye had trouble predicting the path of the object, such as with the unpredictable motion here, the impact of refresh rate was reduced. Content, on the other hand, didn't have an observable impact. We propose a visual model which can directly compare 2 refresh rates and resolution setups, predicting the perceivable quality difference between them. The input is a pair of refresh rate and resolutions for configurations A and B, the velocity of the tracked moving object, and whether such motion is predictable or not. The output on the right is a signed quality difference in JND units, where +1 JND means 75% of the population preferring configuration A over configuration B. Note that the individual frames of the content are not part of the input. We build our model around the worst case scenario of a single line moving left or right, as on the screen. While the proposed application is indeed closely related to the work of De Battista and his colleagues published in 2018, we introduced the motion components, which ultimately allows for dynamically adaptive rendering in the end. The range of velocities we consider also distinguishes us from the concurrently developed work of Shapiro et al., which is coincidentally presented at the same very venue. Furthermore, our proposed model is built on psychophysical components, and therefore we expect that it will generalize to novel viewing conditions, such as different luminance levels, viewing distances, better than the alternatives. The 2 core components of the model are the blur and the judder components. For blur, we distinguish between blurring occurring orthogonal to the direction of motion and parallel or aligned with the direction of motion. This is required as blur is anisotropic in this setup. Orthogonal blur is introduced by the resolution reduction only, while parallel blur is a combination of that and of motion blur. We actually model blur as a combination of three factors: the irregularities in eye motion, the Hall type blur created by the display's discrete stationary samples and the eye spanning over them, and blurring just due to the low resolution of the display. We actually measured the retinal blur with an eye tracker. On the plot, the red line shows gaze location, the blue line shows the hypothetical object location, and the green line shows the sampled location. The eye then integrates over these in the temporal domain, creating a blurry signal. And in the model, we estimate this blur factor as a convolution with a Gaussian kernel. In the model, we estimate each blur factor as a convolution with a Gaussian kernel and describe the final blur as a single combined width of the combined Gaussian kernel. Given two blur sigmas, we estimate the perceived quality difference by taking the Fourier transform of each Gaussian blur kernel, which is again a Gaussian kernel. Then we modulate by the contrast sensitivity function of the eye. We then sample this modulated signal at multiple frequencies and then compute the energy in the signal. These energy differences can be actually interpreted as quality differences. For JUDDER, the visibility of JUDDER artifacts can be predicted by transforming the signal again to the frequency domain. The Fourier transform of perfect motion in the spatiotemporal domain is a single horizontal line. Now, discrete sampling results in false copies of the original spectrum, and the severity of JUDDER can be explained by the location of such false copies. On the right side, you can see the blue diamond representing the region perceivable by human observers, modeled using Watson's window of visibility. In our model, we take the center of the first aliasing copy and compute the contrast sensitivity function at that spatiotemporal frequency. So to summarize, we compute JUDDER quality and blur quality separately, but with two similar pipelines. First, taking the signal to the frequency domain, modulating with the contrast sensitivity function of the eye, and then turning it into quality differences. Three parameters of the model, such as the final weight factors, were fitted to psychophysical data collected in the first experiment, to eye tracking data, and to follow-up pairwise comparison experiments. De Battista et al. Demonstrated that resolution can be traded off for refresh rate in video games when there's a fixed budget. Now, with our visual model, we can trade off for the maximal perceived quality to be applied in real time, thus enabling motion adaptive refresh rate and resolution rendering, or MARRR for short. In our implementation, we input the device limitations such as the rendering budget in millions of pixels per second, and the maximum resolution and the refresh rate of the display. We subsequently compute a lookup table offline, and during rendering, we use this lookup table to suggest a resolution and refresh rate pair based on the current object motion. In practice, we use a combination of mouse motion and eye motion to estimate the tracked object motion. We conducted two sets of validation experiments. For the first experiment, we used photographic content. Users could pan the photographs using the mouse, or it moved in an unpredictable motion. We found that for predictable motion, MARRR was picked significantly more frequently than previous non-motion adaptive methods. For unpredictable motion, we hit some constraints with G-Sync, and some of the results for higher computational budgets were inconclusive. For video game content, we evaluated for two common camera views: a first-person camera mode, where the player only saw a gun and could explore the map at their own pace, and a bird's-eye view, which resembles a simulator or strategy-style game. We found that motion-adaptive rendering was strongly preferred over traditional rendering methods. In conclusion, we presented a visual model taking both blur and judder into account. We demonstrated a novel application of this model with motion adaptive resolution and refresh rate rendering, showing that we can trade off resolution for refresh rate in real time. Some limitations we would like to highlight nonetheless is that the model only incorporates 2 motion artifacts. Adding the other 2, being flicker and ghosting, would yield a more complete predictor. Adding content awareness would also benefit accuracy, especially when dealing with low contrast content, which would require less conservative estimates than our single line high contrast, single pixel high contrast line. For the application, we ought to mention that while we did manage to make G-sync and FreeSync, make use of G-sync and FreeSync in our research, their control system is not really designed for our application. With that, I would like to thank you for your attention. We hope you will enjoy reading our paper and feel free to reach out to us if you have any questions. We hope to see you live again very soon.